Okay, so welcome to video 5 in our course G02 on genome assembly. Now we're going to talk about key concepts in assembly, and we'll go through some exercises so that you can try some of the exercises that are on that sheet in the N drive and on absorb yourself. So an example of this is that we're going to construct a Devon graph from these reads. So the first thing that we have to do for each of these reads is split them up into k-mers. So we might try, for example, here, given their size, like k equals 4. If we have k equals 2, we would have many k-mers that wouldn't really resolve very well. If k-mers equals 5, then it may not resolve properly either. Let's try 4. So we take the first read, so we're going to split it up into C, C, G, G, and then the next one along is going to be C, G, G, A, and then the last one is going to be G, G, A, G. And then repeat this for the next read. That's going to be A, C, C. Then we got A, C, C, G. Then C, C, G, G. And then the final read, we have C, C, G, G. Then we have C, G, G, T. And the last one is going to be G, G, T, T. So to think of then, what reads are unique within this set? So if we look at the top one, we have C, C, G, G, and we also have that down here. So we don't actually need this read at all. What else do we have? We have C, C, G, G here as well. So that's not needed. That's not unique. And then we have other ones that are unique. I'm not sure. So let's try join them together. I'm going to use a different color pen if my computer will work. Maybe not. Okay, we'll stick with red. So you can see there that AAC joins onto this one down here, and this one joins onto this one over here. We know that that joins onto that, and that joins onto that. We also knows that that one joins onto that. I also know that this one also joins onto this. Oh, slightly meandering path. This one down here. And then we can look at other instances where they might overlap. However, I don't think I see any here. They're going to overlap in that way. So using these paths, we can kind of reconstruct as a single path. So we might start with A, C, C connects to A, C, C, G, and that connects to our one above, C, C, G, G, and that connects, that's a G there, to C, G, G, A, and that connects to G, G, A, G here, but also C, 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 G also connects to this one down here, which is C, that's a C, G, G, T, and the one further down, G, G, T, T, and those two don't connect at all. Because the k-mer overlap for G, T, T, there's none at all there. So that means you actually have two paths here. So from these reads, you actually have two contexts that are resolved. You have one, the first path, that's this one here. And then the second path here. So you got A, C, C, G, G. So A, C, 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 G, G, A, G. And then the second one is A, C, C, G, T. Sorry, G, G, T, T. So that means we have two contexts that are possible here, but we don't have evidence that these reads overlap to resolve them into one. However, we could reconstruct these for k equals 3, or indeed k equals 5, and see if we get the same assembly. If we get the same assembly, that gives us more confidence. If we don't get the same assembly, then we have to think about which is the best assembly. So you can try those yourself to see if you get a similar answer. Another example is if we have k-mers like this, we can assemble them into words potentially. But this is a more complex one where you have lots of redundancy between the different ones. but we are assisted because we can kind of work out in our heads what the words might be. So if we start over here with words like Anna, it's a random start really. We can see that there's overlap, say for Ollie, we got 2 Ollies, and then we got 2 licks. And then what else do we have? We've got 2 balls, so we don't need those. We're getting rid of our unique ones. Abo, we got 2 of them there. Tab, we have 2 of them. There's another arrow over here. So they are possibly unique now. So let's start with going to join Anna. So Anna and Nab joined by 2 letters. And then Nab as AB, so that joins to this one up here, and so on. We're going to iterate through that. So Anna, Nab. Then we have Abo. And that connects to all. So let's X them off because we've got them done. Before I forget, we've got 2 Ollies as well, so that's out. So then we've got Ollie again. And then we got Li, we got Liz, and Lick. So you got 2 options there. So you got Liz and Lick, and then you've got Ism. So you have Ball is already there. Then what's left? Met, Etta, Cat, and Tab. So Etta, Tab, where's Tab? Tab is there. So let's Tab joins onto this one here potentially. So we could have catabolism up here, let's say. Cat. I'm missing that. So atta is missing, but there probably is an atta there. So tab connects down here. Atta should be present. And then we have met and etta. And that connects to tab as well. So you see this is kind of our reconstructed graph, and we could try to simplify that. So you have kata connecting to tab, and then meta also connects to that as well. And then we got a nab, ana connects to abo with an I. And then we got 2 connections here. We got lism and lick. So that's our kind of our consistency to 1 graph for these k-mer lanes of 3. But you can also try if for k-mer equals 4 and see what you got if you divided these words up. So you can sort of see that here graphically. You can divide them into k-mers, get the unique ones, and then connect them together. So you can sort of see that laid out there. Atta was up here at the top. I missed it. There we go. So then you can try that yourself for k equals 4. Can you represent these as a graph? We can do the same for these ones. So these are 2 reads, and we're asked for k-mer equals 3. So we just divide them up in the same way we had before. Okay, so let's look at the k-mers for these sequences. So we can start off with TAT for this read here, and that matches with an AT in the next k-mer ATT, and then we have at the end TTA. You can see there that we have the AT overlapping with this AT, and then this TT overlapping with this TT. In the same way for a read above, we can also write that out in the same way. TAA, A, T, and then ATA. And again, we have the same overlaps of K-1 basis. Then we can see if these k-mers are all unique, and it appears to be the case. And we can also look at the overlaps across the different, the 6 different sequences and see if there's overlaps between the different ones. So we can see there is that this AT also connects down here to this one here, because that starts with AT. And then we have ATT and ATA, so those are different. In the same way, we can see there's no matches for TT. And then for TA, we have this one over here. So we'll go around this way to that one. And then we look at the other matches. For AA, we don't have any. AT, we have this one here. That connects to there. And then TA connects from this one up to this one here. So you can see that we have a kind of a complex picture. So we can look at those matches in more detail. So if we look at this, we can think about how to write it in a manner that maybe simplifies it a bit, but it's quite a complex picture. So you got T, A, T, then A, T, T, and then we have T, T, A here. And these connect directly. If we join on this central one here, we have TAA, AAT, and then ATA. We can add those connections back on. So you have 2 connections from TAT going to these 2 here. And then we've got a connection from TTA to the start of this one. So that one actually, we can bring around here like that. Oh, I'm running out of space on my pad. And that's that connection there. And then from ATA, we can go back to TAT, which is already denoted here. And then we got TAA joining onto TTA, which we have already listed there. And then we have TAT is connected to ATA. Is it? Not yet. So we can have another join. Yeah, we have that join there. And then we can look at the different paths that we could run through these sequences and try to resolve them more effectively. But you can see that we have multiple joins. We have, this is a no degree of 3. This one is 2. This one is 2. So they can be joined together. So that effectively can become ATA. So we connect there like that. This one has a no degree of 2 as well. But this one has a connection of 3. And this one has a connection of 2 as well. So you can see that we've had quite a few different connections. We can't necessarily resolve this because of the odd no degree here. If we look at more examples, and this is taken from Sebastian Smith's slides, if we look at the another way of representing this, we have TAT here starting off here, and that connects with an AT to ATT, which is the first one here, but also by an AT sequence to TTA, which is here, which is the TA at the start. So that one actually is in a sense, could be represented in a circular manner, that we have TAT at the start, the next one is TTA here, and then the last one there is sorry, ATT is the second one, and the last one is TTA. So that could be theoretically circular. Hence, these collections of nodes here. And then down here we have the other k-mers, TAA connecting with the other ones. So you can see how they connect with the ones above us too. And what's represented by the blue lines are the different ways that we can walk through these different paths, and note that that we can also apply this logic to more tractable read sets like this example here that we're going to go through now. So let's look at this. So we have our schemers listed here, TAC, then we got ACA, then we have CAG. I'm going to list them all out vertically for ease of simplicity, and they connect together. Then we got CAG, which is already listed here. We got AGT, which is already listed here, and then we got GTC. So that one could connect onto the ones above, in fact. But this order is arbitrary. We've got AGT, which is already here, GTC, which is already here. Then we got TCA, so that's another one that, as it happens, connects above. CAG is listed here already. So you have these connections. We can represent these on the graph just to remind ourselves of the connections. TCA also connects to CAG, and then we have TCA, CAG, which we have TCA already there, and AGA at the end. So that one also connects to AGA. So you're going to see that we have the graph, in a sense, represented already here, and we can merge some of these nodes like TCA, that's one node. So TACA is one, these first two, that connects to CAG, which can connect to AGA, but also it can connect to AGT. And then we see for AGTs node that we have a connectivity of two nodes for GTC. So that can be added on there. And then when we connect to TCA, because of the CA, can also connect to CAG. So you end up with a connectivity like that. So you can see how the nodes can be kind of merged together if they have nodes of even degree. So we can actually merge this like that and get rid of this stuff here, and that would be our best outcome for this particular collection of nodes in this graph, and that's represented also in another way here, depending on if you want to look at the initial de Bourn graph layout. And if you want to apply these to other things like poems, you can actually do the same thing. So this is a circular poem, so we can think of it as being like a plasmid, and then you can look at the links between them. So for example, you can see that we have and over. So you want a starting node that begins with the word over. So that could connect to this one here, like that. But it also could connect to this one here like that. In the same way, it can connect over here to this. So starting with that node is going to be difficult because it's not unique. If we look at it again, these ones are unique. So that's a starting point. All is unique as well. And we see and is also unique. So you can start to figure out that poem by looking at the unique joins and starting with those nodes of even degree before trying to look at the ones that are more complex. If we look at another example, this is taken from Sebastian Schmidt as well. You can take these reads here and go through the full assembly where the k-mer equals to 4. So we're going to split them into bases of 4 bases long. And if we look at this graph, it may look simple because there's just a single snip here, but if we look at the layout, we might find that there's more complexities here. So we start off with A. I'm going to put it horizontally because we know the joins. AATG joins to ATGC. Then we got TGCA. Then we have CGAG. Then we got C, that's a C. AGT. So CGA, yeah. AGTA. And then we can put another one here, GTA. Where's GTA? The T at the end. And then we'll put a join down here because I'm gonna run out of space. TATG. And that one will connect further to A, T, G, C, and that connects in turn to T, G, C, A, which connects to G, C, A, G, which connects to C, A, G, T, which connects to A, G, T, A, G, T, C. There's a lot of letters. And then we have over here then G, T, C. Where are we? G, T, C, A. And let's continue this. So it's a big one. TCA connects to, TCA, T connects to CAT, G, which connects in turn to ATG, C, which connects to TGC, A, which connects to GCA, G, which connects to CAG, T, which then connects to our first SNPs, which are AGT, T, and AGT, G. So it's two splitting nodes there, and they can continue on their own nodes then, as you would expect, to GTTA, GTTGA, and so on. We have separations in the graph with these SNPs. However, with this graph, we could also look at the matches between the different reads. So if we look at ones starting with AAT, you can see that there aren't actually any here. We do the same with ATG, see if there's any that end in those letters. And there is one here. So these two would actually connect to each other. Are there other ones? And so on and so on. We would iterate through those different options. We also find that if we look further on, there's another ATG over here. So this one also would connect with those one here too. And that makes our graph more complicated. So you can see there, we also have ATG here too. So this would also connect with this node down here. And that makes your graph more complicated when you try to lay it out. So you can see that it's not necessarily straightforward to reveal all the different k-mers. This one also has the same feature, so that would connect to that. That would connect to that. That would also connect over here to this. So you see that these graphs, when you try to actually deal with real sequences, get very more difficult to use. So that's why for this kind of sequence, you might want to use a longer k-mer, maybe of 7 to resolve it, or actually a k-mer that's longer would also work like 9 too. If we look at this example solution, if we have a k-mer length of 3, you can see that we have the same connection issues. That we have this ATG sequence that occurs more than ATG, where are we? 3 times in our sequence, and that connects the different nodes. And you can see it has GCA at the end, and it has GCA there as 2, and here as well. So it's actually a repetitive sequence, hence this construction of the different graphs. So the blue is the true path to here. However, with the Genome graph that's assembled, we don't necessarily know that. So that's a complex graph that is hard to resolve without additional information. And then these are the nodes that separate the SNPs. So you can see that what we're really saying here is that when you create a Genome graph, we have to optimize the k-mer and think about how it joins together and try different k-mers if we get a graph that is not resolvable like this. So although it might sound very complicated, you can think of it really as looking at different routes through a train tube map, trying to figure things out. And sometimes what we find at the end is something that might be more unexpected from what we initially thought we would look at. So please look at the next video on the elements for the practical that we'll be doing on Tuesday and Thursday.